In this video, we're going to talk about related rates. The context here is that all the variables that we see, like x, y, r, etc., will all depend on time. And that's something that's important to keep in mind when we're taking derivatives. So we're going to do a couple of quick warm-up problems just around taking derivatives, and then we'll get into some typical application problems. So here's our first example. We're given this formula v equal 4/3 pi r cubed. So you might recognize that as the volume of a sphere. And the idea here is that r is the radius of the sphere and it depends on time. So what we want to do is find dv by dt. I'm going to cross this part out and we'll actually work through that fresh. So the issue with finding dv by dt is that v right now is not a function of t, it's a function of r. So we'd say, well, to find dv by dt, we would need to use the chain rule. We could start by finding dv by dr. We know how to do that because v is a function of r. Just looking up here, we could take that derivative with respect to r, no problem. But then in order to make this equation here true, we would need to multiply by dr by dt. So just from an algebra point of view, you could imagine the dr's would cancel out, and sure enough, you would have dv by dt on both sides of that equation. So that's what tells us that it's valid to write down this equation. dv by dt is equal to dv by dr times dr by dt. So that's the chain rule. It's not the intuitive version of the chain rule, it's the second version of the chain rule that we said we would see a little bit later on in the course. You could think of that as the algebra version of the chain rule. Okay, so now that we've got that written down, what we can do is actually calculate dv by dr, and that's going to take us to the equation that we've got at the bottom of the page here. So just plugging into this equation, we'd have dv by dt equals, now we're going to calculate dv by dr, so just taking the derivative up here in the usual way. The 3 on the r would come down in front, you'd have 4 pi r squared, so that's how we get this part, and then times dr by dt. So that's the kind of algebra process that we're going to need as we go through our problems today. Let's try one more example along these lines. So let's say we're told that variables x and y depend on t, and what we want to do is find the derivative with respect to t of x squared plus y squared. So again, we're going to need the chain rule. The chain rule comes into play anytime there's a mismatch between the variable that you're differentiating with respect to and the variable that you actually see in your function. So anytime there's a mismatch, there's going to be this chain rule going on. So let's look at the first term. Let's take the derivative of the x squared in the usual way. So we would get 2x, and then we would say, but then we need to multiply by the derivative of the inside function being the actual x. So the derivative of the inside function is dx by dt. And then we move into our second term, take the derivative of y squared in the usual way, you'd get 2y. So that's the derivative of your outside function. The y itself is your inside function. You need to multiply by dy by dt to get our derivatives in terms of t. So this is also the chain rule. This particular presentation of it is the intuitive version of the chain rule because we thought about taking the derivative of the outside function, keeping the inside function the same, and then multiplying by the derivative of the inside function. Both of these first two examples were examples of the chain rule. In the first one, we were thinking more about the algebra version of the chain rule. We'll have slightly different variables in different problems, so we'll be aware of that as we go through our calculations. Whereas for this situation here, I would say that's closer to the intuitive version of the chain rule. So with that in mind, now we can jump into some applied problems for this section. So if we go to the first page of the notes here, the problems are actually written out on the first page. We're going to run through 5 problems in this video. So here's our first problem. A 40-foot ladder leans against a wall with its base sliding away from the wall at 2 feet per minute. How fast is the height of the ladder changing when the base is 24 feet from the wall? So let's try to draw a picture. Let's imagine this is our wall and this is our ladder, let's say. So ladder leaning against the wall. Here's the ground or whatever is supporting the ladder. And let's start to label things. So we know this ladder is 40 feet long. Length of the ladder is not changing through the problem, so that's a constant. But what's happening here is that the base of the ladder is sliding away from the wall. So this point is moving that way. And as the base slides away from the wall, that's actually going to drag the top of the ladder down the wall. Okay, so let's introduce some variables here. Let's call this X and Y. And we know how fast the base is sliding away from the wall. So when we talk about how fast the base is sliding away from the wall, we're actually talking about how fast is X increasing. So when we talk about the rate of change of a variable, in symbols, we would write that dx by dt. So rate of change of X with respect to time. That's 2 feet per minute. Okay, and the question is, how fast is the height of the ladder changing? So that would be dy by dt. dy by dt is what we're trying to find. Rate of change of y. And we want that at the moment when the base is 24 feet from the wall. So at the moment when x equals 24. Now, one thing that is helpful in these physical problems is just thinking about the sign of the derivative. This dx by dt, it's a positive 2 feet per minute. It's positive because x is increasing. So anytime a variable is increasing, the derivative of that variable with respect to time will be positive. If we were in some alternate universe where for some reason the base of the ladder were being pushed towards the wall, then x would be decreasing and you would have a negative number for your derivative. So that's something that we'll keep in mind as we go through all of these problems. All right, so that's the setup. We've pulled all the information out of the question. That means that we don't need to read the problem anymore, and we've got all the information contained in our diagram there. So we're going to run through 4 steps of algebra as to how to solve this type of problem. So let's say step 0 is just pull all the information out of the question, and then the real first step is to write down an equation that relates your variables. Okay, well, presumably the wall is at a right angle to the ground. We'll make that assumption. So that means we've got a right triangle. So an equation that relates our variables would be x squared plus y squared equals 40 squared, just from our Pythagorean theorem. And then once you've got an equation relating your variables, what we're going to do is we're going to take derivatives with respect to time all the way across that equation that we just built. So let's look at this equation here and take d by dt of every single variable. Okay, so if you take the derivative of something like x squared with respect to time, you'd say, well, derivative of the outside function is 2x, but then we need to multiply by the derivative of the inside function with respect to time. Okay, so over on the side, maybe let's just do a little bit of scribbling here. If someone asks you to take the derivative with respect to time of something like t squared, you'd say that's 2t. That's just a regular derivative. But if someone says take the derivative with respect to time of, say, z squared, you'd say, okay, derivative of the outside function is 2z, and then according to the chain rule, I need to multiply by the derivative of the inside function with respect to whatever variable we're working with. So that's something to keep in mind throughout this section. So after that side discussion, let's come back to our equation here and just take derivatives with respect to time. So we'd have 2x times dx by dt plus 2y times dy by dt equals, now derivative of a constant with respect to t is going to be 0. So that's our second step done. And then our third step is to find any missing values that we need to solve the problem. Okay, so let's look at this equation that we just built in step 2 and let's see what we know and what we need to figure out. So what we're ultimately trying to find is dy by dt. So that's what we want. And what we know, well, we know an x value and we know our dx by dt. So we know this and we know that. So that means in order to solve the problem, what we need to do is just solve for y. Okay, so this is going to come down to redrawing the picture that we had. at the beginning of the problem. Remember, we had this 40-foot ladder leaning against the wall. Here's our mystery y value. And remember that we're trying to solve the problem at the moment when the base is 24 feet away from the wall. So we can actually sub in the x value 24, and that will lead us to the y value that goes with that. So according to Pythagorean theorem, 24 squared plus y squared equals 40 squared. If we do a little bit of algebra, y squared is equal to 1024, which means y is either plus or minus 32. Now, because y is a length, we can safely say that y is going to be the positive solution. So y is equal to 32. Okay, so now that we've found that, we can take that, put that into the equation that we built in step 2, and this is where we will solve the problem. So we'll call this step 4, solving. Okay, so look back to the equation that we had from step 2 and just plug everything in. So we know our x value is 24. We know our dx by dt is equal to 2. So that's the rate at which the base is sliding away from the wall. We've got plus 2 times our y value, which was 32, times our mystery dy by dt is equal to 0. Great, so we'll have our answer in just about one step. So we're saying 64 dy by dt is equal to negative 96. And that means that dy by dt is equal to negative 1.5. So a couple comments about this. One thing is that it's always nice to put units on here. So in terms of units, think about what the units of your top variable are. Y is a distance, so it's going to be measured in feet, and time in this problem was being measured in minutes. So that's how we can figure out that our units are feet per minute. Always just look at what your variables are on top and on the bottom, and then that will lead you to your units. The other comment is, notice that this comes out to a negative number. So this is actually negative because y is decreasing. So if the derivative of a certain variable with respect to time is negative, that tells you that that variable y is decreasing. And that makes sense because what's going on here is this ladder is, the base is sliding away from the wall, so the top's going to be sliding down the wall. Therefore, y is getting smaller. So that is our first related rates problem. The idea is that if you know the rate at which one variable is changing and you've got your variables related by an equation, then you can figure out the rate at which another variable is changing, hence the name related rates. So problem 2, when a spherical balloon is inflated, its radius increases by 3 centimeters per second. At what rate is the volume changing when the surface area is 100 pi centimeters squared? Well, before going into this problem, we should make sure that we're familiar with a couple of formulas from geometry. So we've been talking about volume and we've been talking about surface area for a sphere. So let's say volume of a sphere is 4/3 pi r cubed. So that's a formula you should be familiar with from geometry. Surface area of a sphere, you may or may not have seen that formula before, but it is 4 pi r squared. And just a kind of interesting geometry fact. Notice that the surface area of the sphere is actually the derivative of the volume of the sphere. So if you have the volume of the sphere stored away in your head, a good way of remembering the surface area of the sphere is just to say to yourself, oh yeah, it's going to be the derivative of the volume of a sphere. And actually that's true for all of our geometry formulas. The surface area will always be the derivative of the volume. So that's just a little aside to make sure that we're comfortable with the formulas that we need going into this problem. So let's try to pull some of the information out of the problem. We know that the radius is increasing. Okay, so that's the rate of change of the radius with respect to time is 3 centimeters per second. And we want to know at what rate is the volume changing. Okay, so that's rate of change of volume with respect to time that we're trying to find. And we want to do that when the surface area is equal to 100 pi. So that way we've pulled all the information out of the question and we do not need to read the question anymore. So let's call that step 0. Also making sure that we've got the relevant formulas at our fingertips, like volume of a sphere and surface area of a sphere. Okay, so then let's mimic the steps that we went through in the previous problem. First thing that we need is an equation that relates our variables. Okay, so let's think about what our variables are. We're talking about volume and we're talking about radius. So the equation that relates those two is actually just the volume of a sphere. Volume is 4/3 pi r cubed. That relates v and r together. And then we can think about taking a derivative. So step 2, what did we do in step 2 in our previous problem? We took the derivative with respect to time all the way across that equation. So on the left side, we would have dv by dt. On the right side, we would have a chain rule coming into play. So we're just looking at this equation here. On the right side, we would take the derivative with respect to r. So that cube would come down in front, give us 4 pi r squared. And then we'd say, but to make this in terms of time, we need to multiply by the derivative of the inside function. So multiply by dr by dt. So that's the derivative of the outside function, keeping the inside function the same, where r is just that inside function. And then that's the derivative of our inside function with respect to t. Okay, so that's our second step done. And then third step, we need to find any missing values before we can solve the equation. Okay, so let's think about what we know. dv by dt is what we're trying to find. So I'll just circle that and I'll say that's what we want. dr by dt, yes, we were given that in the problem. So we know what this number is. And what we need to find is r. Okay, now let's think about what we know. What were we told in the problem that we haven't used yet? We were told that the surface area at the moment that we're interested in is 100 pi. Now, if we knew a formula for surface area, we could plug it in here and that would lead us to the r value. Okay, so let's look back up at what we said at the top here. Oh yeah, we do have a formula for surface area of a sphere. It's 4 pi r squared. So we're saying 4 pi r squared is equal to 100 pi. Okay, now this problem is a little sneaky. There are a couple of ways you could go here. I guess probably the tried and true way would be you would just chug through this equation and solve for r. So you could do that. But if you're really on the ball here, you're really awake, you might notice in the equation that we're going to plug into, we're actually plugging into 4 pi r squared. And we happen to know that 4 pi r squared is equal to 100 pi. So essentially what we're going to do here is we're just going to say this whole thing is 100 pi. So if you had gone through and you had solved for r, you would figure out that r is equal to 5 and you would go back up and you'd sub r equal 5 in there. That's fine. But you're just doing a bunch of steps that you don't really have to do, because bottom line, all we need to do here is be able to sub into the equation in step 2. Okay, so now we're ready to go. We're going to solve. And the solving always comes from your equation in step 2. So maybe I'll be specific about that. So solve the equation from step 2 is always what you're trying to do. Okay, so let's sub in here dv by dt, what we're trying to find. We've said that the 4 pi r squared is equal to 100 pi. Maybe I'll just highlight that equation from step 2 so you can see what we're subbing into. And then from the beginning of the problem, we had a value for dr by dt. We were told that it was 3 centimeters per second. So let's sub that in. So times 3. So in other words, 300 pi, and then let's think units. So we've got units for our volume would be centimeters cubed, and then units for time, we know that's seconds, because we were told that our radius is increasing at 3 centimeters per second. So our answer is 300 pi. centimeters cubed per second, makes sense that that's a positive number. The fact that this number is positive tells us volume is increasing. If the balloon were being deflated, then we would see a negative number here. Volume would be decreasing. So before we jump into our third problem, just want to make a general comment here. A good general rule, especially when you're thinking about getting ready for a test in calculus, is to know all the geometry formulas that you saw from class. Because a lot of people will feel sort of overwhelmed with the geometry formulas, and they'll say, you know, I've seen a lot of geometry formulas in my life. How am I supposed to know which ones I should be familiar with? So what I say is just know the ones that we used to solve problems from class. So that way you can scan through the problems that we solved in these lecture videos, and then you can know those are the, you know, those are similar to the kinds of problems that I would ask on a test. Volume and surface area of a sphere. We'll also talk about a cone in one of our problems. So just know those formulas that we used in the lecture videos. Here's our third problem. How fast is the slope of the tangent line to this curve changing when x equals 2 if x is increasing by 0.5 units per second? Okay, let's see if we can pull all the information out of the problem. So when we say slope of the tangent line, we can call that m tan, but more naturally, we usually call it y prime or dy by dx, either y prime or dy by dx, but I would say y prime is the simplest notation for that. So y prime is the slope of the tangent line, and we want to know how fast is the slope of the tangent line changing, right? So that's the rate of change of y prime with respect to t. That's what we want. dy prime dt. Okay, now what else do we know? We know the actual formula for y. So y is 4 over 2 plus 5x. So I have a feeling we're going to be taking the derivative of this function y. If we want, we can rewrite that into a more user-friendly form by saying 4 times 2 plus 5x to the negative 1. So just using a negative exponent instead of writing this as a fraction, I think will make life easier. And we also know that we're interested in the point where x equals 2, and we have a sense of how fast x is changing. So the rate of change of x with respect to time is equal to 0.5 units per second. That's positive because we're told that x is increasing. So if x is increasing, dx by dt is positive. If x were decreasing, then dx by dt would be negative. Okay, and then we don't actually need this y prime equals the slope of the tangent line. That was just sort of to make sure that we were conceptually on the right track there. So we've pulled all the information out of the question, and then we're ready to start our first step of the problem. So first step is an equation that's going to relate our different variables together. So the different variables that we're interested in are y prime and x. Okay, so let's think about what equation could relate y prime and x together. Well, if we actually just calculated what y prime is, that would be an equation that relates y prime and x together. Okay, so let's do that by looking at this equation here for y and taking the derivative. So the negative 1 would come down in front, multiply with the 4 to give us negative 4 times 2 plus 5x to the power negative 2. Our power becomes more negative when we take the derivative, and then multiply by the derivative of the inside function, so times 5. So we've got a little chain rule going on there. And then we could clean that up just because we're going to do some further calculation with this. So the 5 and the negative 4 could multiply together, and we could say negative 20 times 2 plus 5x to the power negative 2. Okay, so that's our equation. I'm going to highlight this. So that relates y prime and x together. And second step is we're going to take d by dt of this equation. So on the left side, we will have dy prime by dt. On the right side, we've got another chain rule coming into play. So basically, let's come up with a plan of attack before we actually write this down. We're going to need to calculate dy prime by dx and then multiply that by dx by dt in order to get that in terms of t. So the reason it's a chain rule is because y prime right now involves x, and we're saying, but we don't want the derivative in terms of x, we want it in terms of t. So as an intermediate step, we'll take the derivative of y prime with respect to x, and then we'll say, but to make both sides of this equation true, we'd need to multiply by dx by dt. So I think I will, in fact, just write this down like that. We'll do this over the course of a few steps. So if you're confused at this point, just to convince yourself that you've done this right, you can just mentally imagine the dx's canceling there from the top and the bottom. And you would say, yeah, this equation is true. I do have the same thing on both sides. So that's how we know this is the correct thing to do. So this dy prime by dx, that looks a little intimidating, but it's actually something pretty familiar to us. See, if you take y prime, which is the first derivative of y, and then you take another derivative with respect to x, really all you're saying here is, oh, just take the second derivative of y. That's really all that's saying. The reason we had it written in the d notation is just so that we could set up our chain rule here. But really all we need to do is take that second derivative. Okay, so let's try that. So we're saying dy prime by dt is equal to, let's take the second derivative of y. So we're just looking up at this highlighted stuff here. Let's take the derivative again. So the -2 multiplies with the -20 to give +40. Keep the inside the same. Power gets more negative, so now it's -3, and then we multiply by the derivative of the inside function. Okay, so there was a little chain rule going on there as well, just to get y double prime calculated, and then we still need to multiply by dx by dt. So now we're done taking d by dt, and we'll start to think about missing values. So this is where it's super helpful to have gathered all the information at the beginning of the problem, because the last thing I want to be doing right now is reading the word problem over and over again. Much easier if we just look back at the beginning of the problem and see, what we know. So let's refresh our memories. dy prime by dt is what we're trying to find. What we have is an x value, and we have a dx by dt value. So let's see if that's enough to solve the problem. So this here, that's what we want. We've got x and we've got dx by dt. So in fact, there are no missing values. So none. That's good. This problem was actually complicated enough as is without any missing values. So then step 4, we're going to solve. And specifically, you're solving the equation from step 2. So I'm just going to scroll up one more time to refresh my memory on the actual values. So x was 2, and dx by dt was positive 0.5. So here we go. dy prime by dt is equal to 40 times, we're subbing in x equal 2 into this equation here. So that's going to give us 12 to the -3. Okay, so 40 times 12 to the -3 times 5 times 0.5. So let's just take all that stuff, put it into our calculator. That comes out to about 0.06. And then let's think units. So on top, we're supposed to have the units for y prime. Okay, well, y prime is a slope of the tangent line. And when we talk about slope in the xy plane, that is actually unitless because the x and y axes do not have any natural units. Even if you were measuring x and y in centimeters, let's say, slope is a ratio of y values to x values. So the units would cancel out. You'd have something like centimeters over centimeters, and units cancel out. So usually when we talk about units for slope, we just say units. That's kind of what you do when your units are unitless, and then time being measured in seconds. That's positive, so that tells us that our slope is increasing. Sand is filled into a large cone with radius 5 meters and height 10 meters to form a small cone of sand. Okay, let's see what this looks like. So first you might be thinking, is our cone more positioned like this, or is it more positioned like that? Let's imagine that the sand is being filled in from the top. Okay, so if you were in this situation on the right and sand were dropping in here, then at any point in time you would have a small cone of sand that's actually been filled in. Where if you were in the situation on the left, sand would be filling in here. It'd be filling this bottom region. This bottom shape here is not a cone. So you don't have that scenario here. You actually have the scenario on the right. All right, so we've got this conical shaped container. Sand is dropping in from the top like that. And we know that our large cone, so the container, if you want to think of it that way, the container has a radius of 5 meters and a height of 10 meters. All right, there we go. Let's say that sand, or we're told that sand is filled in at a rate of 10 cubic meters per second. Wow, that is so much sand coming in every second. So that's the rate of change of our volume, dV by dt, how fast the volume is changing. Positive, because the volume is getting bigger, positive 10 cubic meters per second. And we want to figure out at what rate is the sand's radius increasing when it is 2 meters. Okay, so we want dr by dt, rate of change of radius. And then it says when it is 2 meters. Well, what is that referring to? That's referring to the radius. So when the radius is 2 meters. All right, so that's all the information pulled out of the problem. And the first thing we're going to do here is come up with an equation that relates our variables. So the different variables that we have in this problem are volume and radius. Okay, so the equation that's going to relate those two things together is the volume of a cone. So you may or may not remember that from some of your previous courses. It is actually pi over 3 r squared h. So a good way to think of this, if you ever needed the volume of a cylinder, it's pi r squared h, because it's the area of a circle times the height of the cylinder. So I would say volume of a cylinder is kind of a relatively easier one to remember. And then just remember that the volume of a cone is actually 1/3 of that. So you can fit exactly 3 of these right circular cones into a cylinder. That's a good way of remembering volume of a cone. Okay, so the volume formula we're looking for is this volume of a cone, pi over 3 r squared h. That's what we're going to be starting with. Now, normally the second step of our problem would be to take d by dt. And we could go ahead and do that right now, but there's something that's going to be a little difficult or a little annoying to deal with, which is the fact that we have these two different variables multiplied together. We've got r squared times h. So in theory, we could take d by dt and we could do a product rule here. But actually, the easier way to proceed is just to get the h out of the problem sooner. So we're not going to jump the gun. We're not going to go to step 2 yet. We are actually going to eliminate h. And the way we're going to do that is using similar triangles, because we actually have enough information here just to get rid of h right at the beginning of the problem. So whenever you see two different variables being multiplied together, like an r times an h or an r squared h or something, just ask the question, do I have enough information to use similar triangles, and just get rid of one of those variables. So let's do a little side discussion here and figure out how to eliminate h. So the idea is that we actually need a couple more variables in our picture. Let's go back to our picture up at the top of the page. See, at any point in time, we have this small cone of sand, which is in red in our diagram. So let's use variables here. Let's use the variables r and h to represent the radius and the height of the actual cone of sand that we have filled in. So we've got two different radius values and two different height values here. We're talking about the big container having radius and height 5 and 10, whereas at any moment in time, our cone of sand that's been filled in has radius r and h. Now the idea is that one cone is sitting inside the other, right? So if we draw our picture, I'm just going to draw the cone as a cross section, as a triangle here. So you've really got two little right triangles, one sitting inside the other. So this is the sand that has been filled in, whereas the bigger one is the container. Okay, and whenever you have two right triangles, one sitting inside the other, that's the scenario called similar triangles. So let's think about the dimensions here. So r and h for the small cone, and then I'll just do it like this, 5 and 10 for the big one. So the idea with similar triangles is that if you take the ratio of the dimensions, they will be the same for both triangles. So for the big container, it's 5 over 10. For the small cone of sand, it's r over h. So in each case, we're just dividing the radius by the height. Okay, so let's see if we can solve for h. See, if we cross multiplied here, we'd have 5h equals 10r, or in other words, h equals 2r. So what that tells us is that at any point in time, as this sand is being filled in, that small cone of sand will always have the property that the height will be 2 times the radius. So now in a different problem, you might have a different relationship between h and r, right? In a different problem, if the container had a different shape, it could be like h equal 3r throughout the problem, or h equal 4r throughout the problem. But for this particular container of sand, it's going to be h equal 2r throughout this entire problem. So we're going to take this h, we're going to sub it in to this equation and get a new and improved equation. Okay, so instead of saying v equals pi over 3 r squared h, we're going to say it's pi over 3 r squared times 2r, and we might as well just call that v equal 2 pi over 3 r cubed. Okay, and I'm going to put a happy face there because now we've got an h entirely out of the problem, and we've just got a problem involving r and v. So that's beautiful. So consider doing this similar triangles process whenever your equation has a couple of different variables that are multiplied together, like RH or r squared h. So that's the whole first step done, and actually from here the problem's going to flow really pretty nicely. Hard work is done. So step 2, we're going to take d by dt of this equation that we just built. So on the left side, dv by dt. On the right side, take the derivative of the right side. So the cube will come down and multiply with that 1 over 3, just to give us 2 pi. Power on the r will decrease. And then we need to multiply by derivative of the inside function, which is r, with respect to t. Okay, then in step 3, we would ask if there are any missing values. The answer is that there are none. Main reason that there are no missing values is because we did that similar triangles process already in step 1. So no missing values to deal with, and then we can just solve. So we'll just do that over here. So solve the equation from step 2. Let's highlight that. And let's flash back to the top to just figure out our values. So what did we know? We know that dv by dt is equal to 10 cubic meters per second, and we know that r is equal to 2 meters. What we're looking for, dr by dt. Okay, so plugging everything in here, 10 cubic meters per second for the dv by dt. R is equal to 2, so it's 2 pi times 4 times the mystery dr by dt. Can multiply all this stuff together to say it's 8 pi. And then we say dr by dt is equal to 10 over 8 pi, which, if you want to put it into your calculator, is about 0.4. And then units, meters for the radius, and seconds for time. A 12 meter by 20 meter swimming pool is filled at a rate of 4 cubic meters per minute. The ends are 1 meter and 3 meters deep with a constant slope along the bottom. The rate of change of the water depth, or find the rate of change of the water depth when the depth is equal to 1.5 meters. So the fact that there's a question mark at the end of this last sentence just means find the rate of change of the water depth. For this one, I would strongly suggest drawing a picture just because there's a lot of description here of the different dimensions of the swimming pool. So let's try to figure this out. So if we just think about the surface of the swimming pool, it's a rectangle. So it's 12 by 20 in terms of meters. And then the ends are 1 meter and 3 meter deep. Okay, so that means this pool has like a shallow end and a deep end. So the shallow end goes down 1 meter, whereas at the deep end over here, it's actually 3 meters deep. And then they said with a constant slope along the bottom. So that means there's no like drop off or anything like that. It just gradually goes from the shallow end to the deep end. So I would say that's really important is being able to pull all that information out of the question. Okay, so in problems that are kind of big, I'm almost inclined to just kind of cross things off as we've thought about them. So yeah, we know it's 12 by 20 meters. We know the ends are 1 and 3 meters deep with a constant slope along the bottom. Okay, so we've dealt with all of that. The pool is filled at a rate of 4 meters cubed per minute. So that's volume. That's how much volume is going in per amount of time. So rate of change of volume with respect to time equals 4 cubic meters per minute. So we dealt with that. Okay, and then we want the rate of change of the water depth when the depth is equal to 1.5 meters. All right, so we are going to need a variable to talk about that water depth. Maybe let's just draw a second version of the sketch just to introduce a variable here. So here's the top surface of our swimming pool. Here's the shallow end. And here's the deep end. Okay, and then constant slope along the bottom. Now, it doesn't really matter where you're pumping water into this, but water is always going to flow to the lowest point in the swimming pool, right? So as water gets filled in, it's sort of going to be sitting in, just this part of the pool. It's going to be going to the deep end. So what would be good here is just to have a variable for the depth of the water that we've got at any point, and we'd be measuring that depth just from the deepest part of the pool. So let's call that y, since it's a vertical variable. Okay, so we want the rate of change of y with respect to time. We want to figure out what is that when the depth is equal to 1.5. Okay, that way we've pulled everything out of the question. Do not need to look back at that question anymore. So what we're going to need in our first step is an equation that relates volume and y together. One thing I would say we could do here to simplify the problem is just think about a cross section of the swimming pool. So just imagine that you're standing somewhere back here and you're looking at the swimming pool this way. Okay, and imagine what your cross section would look like. So this is going to lead to kind of a simpler picture. So your cross section, well, you'd see 20 meters of water going this way. You'd see 1 meter of swimming pool this way, 3 meters here, and then a constant slope going that way. So 21 and 3. Okay, and then your water is going to be sitting somewhere down here. So we're going to call that y. We know that at the point that we're interested in the problem, the water depth is 1.5. So let's think about this for a minute. If we were to just sort of draw a dotted line, see how the shallow end compares to the deep end, this would be 1 meter, that would be 2 meters. So in fact, we're sort of interested in the point when y gets to be about 1.5 meters. So let's say in our picture, just for the sake of a representative picture so we can visualize what's going on, at the point in time that we're interested in, we've got about that much water in the pool. So this is really helpful for us because that tells us that throughout the entire problem, the volume of water that we've got in the pool, it has a triangular cross section, right? The pool never gets so filled that we get up to this point. That's never going to happen. If we were here, we would have sort of a weird shape of a cross section because it would have this straight side and then it would have a triangle beneath it. But we never get to that point, so we do not have to be concerned about that. Our water always has a nice triangular cross section. So that is going to be super helpful in setting up an equation. So let's actually introduce two variables. We'll call x and y the side lengths of the triangular cross section for how much water we've actually got in the pool. And I'll actually label this stuff here water, just so we are clear what we're looking at in this cross section. So based on that, I bet we can write down a formula for volume. Okay, so what we want is a formula that relates the volume of water in the swimming pool to our different variables like x and y. So let's say volume is going to be the area of the triangle that we're seeing in our picture here, and then times the width of the swimming pool, right? Remember that there was 12 meters of width that we're not seeing in this cross section. So the area of this triangle, this black triangle here representing our water, well, area of a triangle is always going to be half the base times the height. So it's going to be half xy. And then times the width, well, there's 12 meters of width that we're not seeing here. So V comes out to 6xy. Okay, now in our next step, our goal is going to be to take the derivative with respect to time of this equation. But similar to the last problem, we've got this kind of tricky situation where we've got two variables multiplied together, this x and y multiplied together. And whenever that happens, it's sort of inconvenient in terms of taking derivatives. I mean, you could use the product rule and the chain rule to take derivatives with respect to time, but there is a much better way, and that better way is similar triangles. So let's look back at our swimming pool cross section. And let's see if we can find a way to set up similar triangles in this picture. So let's look at the picture that we've got up at the top of the screen here. We said the water level is always going to be such that the water is always touching this slope. The water's never going to be filled as far up that it will be touching the left side of the pool. So therefore, we basically don't care about the top 1 meter of this picture, right? We just really care about this triangle here, which covers the bottom 2 meters of the swimming pool. And that's going to be a similar triangle with the triangular cross-section of water that we've actually got filled in. So let's draw our similar triangles here. So big triangle covers the bottom 2 meters of the pool, and it's 20 meters long. And that's a similar triangle to the triangle of water that we've actually got filled into the pool, which is going to have dimensions x and y. So according to similar triangles then, you can say 20 over 2 is going to be the same thing as x over y. If you just make that 20 over 2 equal to 10, that's saying by cross multiplying 10y is equal to x, or in other words, x equals 10y. So we're then going to take that x equal 10y, are going to plug that in to our formula for volume to get a new and improved volume formula. So what comes out at the end of this first step, we get this nice volume formula. Go write it over on the left side here. Volume is equal to 6x times y, but we're saying that x is equal to 10y. So volume equals 60y squared is what we've figured out. So let's just run through what we've done so far. We drew a few different pictures of our swimming pool. I would say the most important picture by far is this one here, where we decided just to think about a cross section of the pool. And most importantly, we realized that the water throughout the problem would be just forming a triangular cross section. So that allowed us to find the volume of the water in the pool in terms of x and y. And then we've just now used similar triangles. So we did our similar triangle reasoning in this box. and then we plugged into that volume to figure out that volume is equal to 60y squared. So that is the hard part of the problem done, and then we've got 2 more quite quick steps to go to finish off the problem. So I'm just continuing on a new page here. We were doing step 1, finding the equation. We did a bunch of work and we found that the volume was equal to 60y squared. So now step 2 is to take d by dt of this equation here. So on the left side, we'd have dv by dt. On the right side, take the derivative of the outside function, which is 120y, and then multiply by the derivative of the inside function. So the inside function being the y. So we need to go dy by dt in order to get that in terms of time. Okay, now for step 3, if there were any missing values, we would find those here, but there are none. And the main reason there are none is that we chose to do similar triangles earlier in the problem. So we've actually got a nice equation that we're ready to solve for. So you can see making the time investment to do similar triangles at the beginning of the problem, really pays off at the end of the problem. Okay, so now we're going to solve, and when we say solve, it's always the equation from step 2 that you're trying to solve. So let's just flash back to our previous page. We'll remind ourselves what our values were. So the values we're going to need, dv by dt is 4 and y is equal to 1.5. What we're trying to find is dy by dt. Okay, so plugging into our highlighted equation, 4 equals 120 times 1.5 times this dy by dt value that we're trying to solve for. 120 by 1.5 is 180, so we can say dy by dt is equal to 4 over 180, or approximately 0.02. In terms of units, y is the depth that was measured in meters, and time in this problem was measured in minutes. So that's about 0.02 meters per minute. So just as a summary of this section, I would say questions 4 and 5 were a little different than the first 3 because questions 4 and 5 involved doing similar triangles in step 1 where we were setting up the equation. So that's all about related rates. Thanks for watching.